Right now, the scientific community is counting down to December 19th, 2025, the date that will settle a debate dividing planetologists into two camps. On that day, 3I Atlas will pass Earth at a distance of 270 million kilometers, and the James Webb Space Telescope will have a 48-hour window to answer a question that has haunted researchers since perihelion. Are we looking at an unusual comet or the first naturally delivered sample of exoplanetary material in human history? The silence from NASA's imaging teams has become conspicuous. More than a month has passed since perihelion on October 30th, and high-resolution Hubble images that should reveal surface features down to a few hundred meters remain unpublished, labeled as under analysis. For an object that defied every standard comet model by losing its tail despite calculations showing it should have shed 13% of its total mass, billions of tons of gas and dust, into space, this delay feels less like bureaucratic routine and more like scientific caution in the face of something unexpected. What makes 3I Atlas so unsettling is not any single anomaly, but the accumulation of contradictions. The object brightened threefold more than predicted during perihelion passage, yet remained compact, with no diffuse envelope, no debris trail, just a tight greenish point of light moving against the stars. Spectroscopic analysis revealed carbon dioxide concentrations exceeding 30% of the volatile inventory, far above the typical 5 to 15% found in comets. Carbon dioxide sublimates at extremely low temperatures, around 148 Kelvin, meaning an object this rich in CO2 should outgas furiously under solar heating, producing exactly the kind of spectacular tail that failed to appear. Non-gravitational acceleration measurements confirmed that outgassing was occurring. The escaping material exerted enough thrust to nudge the object off its purely gravitational trajectory, but the magnitude didn't correlate with observed brightness or inferred mass loss. The thrust appeared stronger than visible outgassing warranted, suggesting hidden gas emissions from the night side or interior reservoirs venting through subsurface conduits. Either scenario departs fundamentally from the standard rubble pile model of cometary nuclei. Emily Saunders, a planetologist with NASA's Solar System Exploration Division, framed the puzzle carefully. This is like deciphering a fragment from another star system where chemical and physical conditions radically differed from ours. The phrasing acknowledged uncertainty while hinting at scale. If 3I Atlas formed in a protoplanetary disk around another star, its composition would reflect that environment's specific chemistry and temperature gradients. Stars vary in metallicity, the abundance of elements heavier than helium, and protoplanetary disks mirror those differences. A disk rich in carbon relative to oxygen would produce carbon-rich ices and minerals instead of the silicates and water ice common in our solar system. Avi Loeb, the Harvard astrophysicist known for unconventional hypotheses regarding interstellar objects, offered a more provocative interpretation. The anomalies, brightness behavior, CO2 dominance, non-gravitational acceleration inconsistent with visible outgassing, might indicate layered internal structure akin to geological strata in a terrestrial planet. What if it is not just a comet, Loeb suggested, but a fragment of a long-destroyed exoplanet carrying secrets aged 7.5 billion years? The age estimate derived from isotopic modeling of the CO2 spectrum, which showed depletion patterns consistent with materials formed in the early universe, roughly 3 billion years before our Sun coalesced from its own molecular cloud. Stop and consider that. The Sun is 4.6 billion years old. Earth formed shortly after, cooling and differentiating over a few hundred million years. If 3I Atlas originated 7.5 billion years ago in a protoplanetary disk that has since dispersed, the parent star might have evolved off the main sequence, possibly dying as a white dwarf or even detonating as a supernova. The planetary system that birthed this object could be gone, erased by stellar evolution or torn apart by a close encounter with another star during a passage through the galactic disk. What survived would be fragments, shards of rock and ice flung into interstellar space, drifting for eons until chance brought one into our neighborhood. Read between the lines of the scientific statements. When researchers say radically different conditions, they are acknowledging that the chemistry recorded in 3I Atlas does not match solar system norms. When they describe layered structure, they imply differential composition with depth, like sedimentary rock or metamorphic formations. Earth's geology preserves a record of changing environmental conditions over billions of years. Ancient oceans, volcanic episodes, tectonic collisions. Could an exoplanet fragment carry a similar archive? If 3I Atlas is indeed a shard of a destroyed world, its interior layers might record the chemical evolution of an alien planet, frozen in time and delivered to our doorstep by the random walk of interstellar trajectories. The greenish glow that observers reported immediately after discovery comes from diatomic carbon, C2, fluorescing at around 518 nanometers wavelength. This emission arises when sunlight breaks apart larger carbon molecules on the surface, and the fragments radiate as they decay back to lower energy states. Strong green coloration implies carbon-rich ices, possibly carbon monoxide, methane, or more complex organics. But the spectrum also showed something unexpected, a shift toward the blue range, meaning shorter wavelengths were more prominent than expected. This could indicate a change in composition as surface layers ablated away, exposing deeper material with different chemical makeup, or it might reflect scattering effects from fine dust grains. Carbon dioxide absorption bands appeared at 2.7 microns, 4.3 microns, and 15 microns in infrared observations. The strength of these features indicated CO2 abundance exceeding 30% by mass in the near-surface layers. For comparison, Earth's atmosphere is 0.04% CO2 by volume. Mars is 95% CO2, but at low pressure. In comets, CO2 typically constitutes a minor component, far less than water ice. High CO2 concentration implies formation beyond the snow line, the distance from a star where temperatures drop low enough for carbon dioxide to condense as ice. In our solar system, the CO2 snow line sits around 10 astronomical units from the Sun, beyond Jupiter's orbit. An object rich in CO2 likely formed in the cold outer regions of its birth disk, where temperatures hovered around 50 to 100 Kelvin. Think about what that means. If 3I Atlas formed in the frigid outskirts of an exoplanetary system, it should behave predictably. Approach the Sun, heat up, outgas violently, develop a tail, fade as volatile ices deplete. Instead, it brightened more than expected and remained compact. The combination suggests a thermal or structural property that current models overlook. One possibility, subsurface insulation. If the outer layers consisted of low thermal conductivity material, porous rock, carbon-rich dust, or refractory organics, heat from sunlight would penetrate slowly, allowing the surface to reach high temperatures while the interior stayed cold. Sublimating CO2 beneath this insulating crust could vent through cracks or fractures, producing jets that carried less dust than typical comets. Observers viewing from certain angles might miss the jets entirely, explaining the absence of a visible tail. Another possibility cuts deeper. The object is not a pristine comet, but a fragment with internal structure inherited from a planetary origin. Imagine an exoplanet, perhaps Earth-sized or larger, orbiting a star in the habitable zone or farther out. Over hundreds of millions of years it differentiates, heavy metals sink to form an iron core, silicate mantle forms above, crust solidifies on top. Volatiles, water, carbon dioxide, nitrogen, condense on the surface or get incorporated into minerals. Then catastrophe strikes. A giant planet migrates inward due to interactions with a remnant protoplanetary disk, its gravity perturbing the smaller world's orbit. Tidal forces stretch the planet, raising internal temperatures, possibly triggering volcanism. Eventually, the orbit becomes unstable. The planet either plunges into the star or gets ejected into interstellar space. Alternatively, a close encounter with another star during a passage through a dense stellar cluster could gravitationally disrupt the system, tearing planets from their orbits and fragmenting them in the process. Ejection into interstellar space freezes the fragment. Surface temperatures drop to around 10 Kelvin, just above absolute zero. Any residual heat from the planet's formation or tidal heating radiates away over millions of years. The shard becomes an inert block of rock and ice, drifting through the galaxy at tens of kilometers per second. After billions of years, the fragment encounters our solar system by chance. Gravitational interaction with the Sun accelerates it inward, heating the surface for the first time in eons. If the fragment retained layered structure from its planetary origin, ice-rich outer layers over a rocky core, the thermal response would differ from a homogeneous comet. The ice sublimates, but the underlying rock provides structural support, preventing the nucleus from fragmenting. Outgassing occurs through fractures in the crust, producing jets rather than uniform evaporation. This hypothesis, while speculative, addresses several anomalies simultaneously. It explains the high CO2 concentration. If the fragment came from an exoplanet's icy crust, CO2 ice would be abundant, condensed from a primordial atmosphere. It accounts for the missing tail. Localized jets from fractures might not produce a visible coma if the viewing geometry was unfavorable or if the dust content was unusually low. It rationalizes the non-gravitational acceleration. Venting gas from subsurface reservoirs could exert thrust without creating obvious surface activity. It makes sense of the brightness increase. As the insulating crust heated and fractured, more surface area became exposed to sunlight, boosting reflectivity and gas production. And it fits the age estimate. A 7.5 billion-year-old fragment would predate the solar system, originating in an earlier generation of star and planet formation. Polarimetric observations added another wrinkle to the mystery. When sunlight reflects off a surface, it becomes partially polarized, meaning the electric field oscillations align preferentially in certain directions. The degree and orientation of polarization depend on the surface material, grain size, and viewing angle. Comets typically show polarization consistent with micron-sized dust grains composed of silicates and organics. 3I Atlas exhibited polarization properties closer to larger grains, perhaps tens of microns, or to surfaces with unusual roughness. This could indicate a regolith, a layer of fragmented rock and ice, similar to the surfaces of asteroids or planetary moons. If confirmed, it would support the fragment hypothesis. A shard of an exoplanet would possess a rubble-covered surface from impact gardening over billions of years, quite different from the fluffy, pristine ice of a freshly formed comet. Trajectory analysis revealed another curiosity. Most interstellar objects approach the solar system from random directions, reflecting the isotropic distribution of stars in the galaxy. 3I Atlas, however, entered the ecliptic plane at a relatively low angle, almost as if it were part of the solar system's architecture. This could be coincidence. Statistical flukes happen, but it might hint at a specific origin. If 3I Atlas was ejected from a planetary system passing through the galactic neighborhood a few million years ago, its velocity vector could align with the local standard of rest, the average motion of stars in our part of the galaxy. Such alignment would reduce the relative velocity and make low-angle encounters more probable, potentially allowing the object to linger longer in the inner solar system. The December 19th flyby represents the critical observational window. At 270 million kilometers from Earth, roughly 1.8 astronomical units, 3I Atlas will be far enough from the Sun to reduce thermal noise that complicated perihelion observations, yet close enough for detailed study. The James Webb Space Telescope, positioned at the second Lagrange point 1.5 million kilometers from Earth, can dedicate its infrared instruments without solar interference. JWST's near-infrared spectrograph can resolve absorption features from water, methane, ammonia, and complex organics down to parts per million sensitivity. Its mid-infrared camera can map surface temperature distributions, identifying hotspots from active venting or residual thermal inertia from subsurface heat sources. JWST will allocate 20 hours of observation time split between near-infrared spectroscopy and mid-infrared imaging. The near-infrared spectrograph will collect light across wavelengths from 0.6 to 5.3 microns, capturing absorption features from water, CO2, methane, ammonia, and complex organics. Integration time will span several hours per target, split across multiple configurations to cover the full spectral range. The resulting spectra will have signal-to-noise ratios exceeding 100, sufficient to detect trace constituents at the parts per million level. Mid-infrared imaging will map the object's thermal emission, revealing temperature variations across the surface. Hotspots would indicate active venting or subsurface heat. Cold regions might correspond to shadowed craters or compositionally distinct areas with different thermal inertia. The spatial resolution will be about 1 kilometer at the object's distance, enough to resolve large-scale features but not fine details. European Southern Observatory facilities in Chile will coordinate ground-based spectroscopy during the December approach, using the Very Large Telescope's adaptive optics to achieve near-diffraction limited imaging. VLT can resolve the object into a disk rather than a point source, allowing surface features to be mapped if the contrast is sufficient. Spectropolarimetry will refine the grain size and composition estimates. Greenbank and ALMA could attempt long-integration imaging if the object shows unexpected radio emissions, a long shot, but justified given the anomalies already observed. If 3I Atlas is indeed a planetary fragment, the December flyby could reveal diagnostic signatures. Layered composition would show as spectral variations across the surface, with different minerals or ices exposed in different regions. Impact craters, if present and large enough, might be detectable as albedo variations or thermal anomalies. If the fragment retains remnant internal heat from tidal disruption or radioactive decay, infrared imaging could detect thermal emission exceeding solar equilibrium temperatures. Any of these findings would elevate the hypothesis from speculation to serious consideration. Conversely, if the observations show a uniform, homogeneous composition consistent with a comet nucleus, the fragment hypothesis loses traction. The anomalies would then require explanation within the standard comet framework, unusual composition, atypical structure, or rare viewing geometry. Science advances through exactly this process. Propose a hypothesis, test predictions, refine or discard based on evidence. The December observations will provide the evidence. Consider the broader implications if the fragment hypothesis holds. Exoplanetary science has cataloged over 5,000 confirmed planets beyond the solar system, ranging from hot Jupiters to rocky super-Earths to ice giants. All of these detections come from indirect methods: radial velocity shifts, transit photometry, gravitational microlensing. Direct imaging has captured a few dozen planets, mostly young gas giants glowing in infrared from residual formation heat. No mission has yet returned a sample of exoplanetary material for laboratory analysis. If 3I Atlas is a fragment of an exoplanet, it would be the first physical sample of another world beyond our solar system delivered naturally to our vicinity. The scientific value would be immeasurable. Geochemical analysis of meteorites revolutionized our understanding of solar system formation. Carbonaceous chondrites, the most primitive meteorites, preserve grains older than the Sun, isotopic anomalies from nearby supernovae, and organic molecules that seeded prebiotic chemistry on Earth. A fragment of an exoplanet would offer similar insights into alien geochemistry. The isotopic ratios of carbon, oxygen, nitrogen, and heavier elements would trace the stellar nucleosynthesis that built the parent star. Mineral phases would reveal the pressure and temperature history of planetary differentiation. Organic molecules, if present, would test whether carbon-based chemistry follows universal pathways or varies wildly between star systems. Discovery of amino acids, nucleobases, or other prebiotic compounds would sharpen the question of life's prevalence in the galaxy. Even if no organics appear, the mineralogy alone would break new ground. Earth's mantle contains olivine, pyroxene, and garnet, magnesium-iron silicates forged at high pressure and temperature. A carbon-rich exoplanet might produce silicon carbide, graphite, or even diamond in its interior. Spectroscopic detection of these minerals in 3I Atlas would confirm exotic planetary environments where carbon chemistry dominates over silicon-oxygen bonds. Such conditions are predicted in planets orbiting carbon-rich stars, where the protoplanetary disk has more carbon than oxygen, reversing the usual silicate-dominated composition. The hypothesis raises another tantalizing prospect. If 3I Atlas is a fragment, how many more exist? Planetary system formation is violent. Gravitational interactions between protoplanets lead to collisions and ejections. Numerical simulations of solar system formation suggest that dozens of Mars-sized embryos formed in the inner disk, and most were either accreted into Earth and Venus or thrown into interstellar space by Jupiter's gravity. If this pattern holds generally, every planetary system should eject a population of fragments during its formative years. Multiply by the hundreds of billions of stars in the galaxy, and the interstellar medium becomes littered with planetary debris. Most would be undetectable, dark and silent, drifting at 20 to 50 kilometers per second. Occasionally, one would pass through another star's system, offering a fleeting glimpse of alien geology. Detection statistics support this picture tentatively. 2 confirmed interstellar objects preceded 3I Atlas. 1I Oumuamua in 2017 and 2I Borisov in 2019. Oumuamua exhibited extreme elongation, tumbling rotation, and unexplained non-gravitational acceleration, sparking hypotheses ranging from nitrogen icebergs to artificial probes. Borisov looked and behaved like a comet, outgassing carbon monoxide and showing a normal coma and tail. The diversity suggests multiple origins. Borisov, likely a pristine comet ejected from another Kuiper belt, Oumuamua, possibly a fragment or something more exotic, and now 3I Atlas, with characteristics intermediate between the two. Surveys like the Vera Rubin Observatory, set to begin operations in 2025, will detect interstellar interlopers at a rate of 1 per year, possibly more. Building a statistical sample will clarify whether fragments are common or rare, whether compositions cluster around certain types, and whether any correlate with nearby stellar populations. The scientific community has debated these questions in preprint servers and conference presentations through October and November. Some researchers argued the entire mystery dissolved under closer scrutiny. The CO2 sublimation could occur preferentially on the night side, where shadowed ice radiates heat to space more slowly, allowing gas to escape without forming a sunlit coma. Others proposed that the object's trajectory placed it nearly edge-on to Earth observers during perihelion, making any tail appear foreshortened and faint. Still others suggested that the dust-to-gas ratio in 3I Atlas was extraordinarily low, perhaps 1/100th the typical value, rendering the tail invisible even if outgassing was vigorous. Each explanation had merit. None fully satisfied the data. Emily Saunders, in a follow-up interview, clarified her earlier statement. "We are treating 3I Atlas as an opportunity to study a pristine sample from another star system. Whether it is a comet or a fragment remains an open question. The data will decide." The phrasing acknowledges both possibilities without favoring either. Loeb, characteristically bolder, pressed the case in a preprint submitted to the Astrophysical Journal Letters. "The combination of high CO2 abundance, layered polarimetric properties, and absence of a classical coma is difficult to reconcile with standard comet models and warrants consideration of alternative scenarios, including planetary fragments." The phrasing was carefully calibrated, avoiding the more controversial suggestions that had drawn pushback in the case of Oumuamua, while still advocating for serious consideration of the fragment hypothesis. The age estimate of 7.5 billion years derives from modeling the CO2 isotopic ratios. Carbon has two stable isotopes, carbon-12 and carbon-13. The ratio between them depends on the nuclear processes in the star that produced the carbon and on subsequent chemical fractionation. Young stars formed from gas enriched by multiple generations of supernovae have higher carbon-13 abundances than older stars formed from less processed material. By comparing the measured carbon-13 to carbon-12 ratio in 3I Atlas to models of galactic chemical evolution, researchers estimated the formation epoch. The calculation assumes the CO2 has not undergone significant isotopic exchange since formation, a reasonable assumption for material frozen at 10 Kelvin for billions of years. Oxygen isotopes provide a cross-check. Oxygen has three stable isotopes: oxygen-16, oxygen-17, and oxygen-18. The ratios among them trace nucleosynthesis in massive stars and mixing in the interstellar medium. If the oxygen isotopic composition in 3I Atlas's CO2 matches the carbon isotopes in pointing to a 7.5 billion year formation age, confidence in the estimate increases. Preliminary spectroscopy hinted at oxygen-17 enrichment, consistent with old stellar populations, but the signal-to-noise ratio was marginal. JWST observations in December should resolve the oxygen isotopes definitively, either confirming the ancient origin or revealing a younger, solar system-like composition. The possibility that 3I Atlas predates the Sun by 3 billion years forces contemplation of deep time. The universe is 13.8 billion years old. The first stars ignited around 200 million years after the Big Bang, massive and short-lived, seeding the cosmos with heavy elements through supernovae. Second-generation stars formed from enriched gas around 12 to 13 billion years ago, and some of those stars likely hosted planets. By 7.5 billion years ago, the galaxy teemed with mature planetary systems, many of which have since been destroyed or dispersed. A fragment from that era, is a messenger from an epoch when the Milky Way was younger, star formation rates higher, and the conditions for planet formation potentially different from today. If life exists elsewhere in the galaxy, it might have arisen in those ancient systems. Planets orbiting sun-like stars enjoy habitable conditions for billions of years. A planet that formed 7.5 billion years ago and remained stable could have hosted life for longer than Earth has existed. If that planet was destroyed and fragments ejected, could any biological signatures survive? Probably not. Cosmic radiation would sterilize exposed surfaces over millions of years, breaking down complex organics into simpler compounds. Deep within a fragment, shielded by meters of rock, some molecules might persist, but detecting them would require landing a probe and drilling far beyond current capabilities for a fast-moving interstellar object. Nevertheless, the prospect tantalizes. Panspermia, the idea that life spreads between star systems via comets or asteroids, remains speculative but not ruled out. If microbial life or its chemical precursors were common in the early galaxy, ejected fragments could have seeded many worlds, including Earth. Testing this idea requires finding organic molecules in interstellar objects and comparing them to terrestrial biochemistry. So far, no interstellar object has been studied closely enough to detect organics. 3I Atlas might change that if JWST spectroscopy reveals absorption bands from methane, formaldehyde, or more complex molecules. March 16, 2026, brings another observational opportunity. On that date, 3I Atlas will pass Jupiter at a distance of roughly 50 million kilometers, close enough for the giant planet's gravity to perturb the trajectory measurably. Tracking the deflection will refine the mass estimate, which currently relies on assumed density. If the object is a dense rocky fragment, its mass will be higher than if it is a porous comet. The gravitational deflection scales with mass, so precise astrometry before and after the Jupiter flyby will constrain the density to within 10%. A density exceeding 2 grams per cubic centimeter would favor the fragment hypothesis. Below 1 gram per cubic centimeter would support the comet model. The Jupiter encounter also poses a risk. If 3I Atlas passes too close, tidal forces could fragment the object. Jupiter's gravity creates a tidal stress gradient across any extended body, compressing along one axis and stretching along the other. A loosely bound comet nucleus might disintegrate, as comet Shoemaker-Levy 9 did when it approached Jupiter in 1992, breaking into a chain of fragments that later impacted the planet. If 3I Atlas survives the encounter intact, it would indicate significant internal strength, more consistent with a coherent rock fragment than a rubble pile. Assuming survival, the object will exit the solar system on a hyperbolic trajectory, accelerating outward past Saturn's orbit and into the Kuiper belt, eventually crossing the heliopause and returning to interstellar space. The entire visit will span less than 2 years from discovery to departure, a brief window to gather data. No mission is currently capable of intercepting 3I Atlas. A spacecraft would need to launch soon to match its velocity, requiring delta-V far exceeding any existing propulsion system. Proposals exist for rapid-response interstellar intercept missions using solar sails or nuclear propulsion, but none have moved past the concept stage. The object will slip away unsampled, leaving only remote sensing data and unanswered questions. This raises a philosophical point. Humanity's ability to detect interstellar objects has outpaced its ability to study them up close. Telescopes find these visitors months or even years after they pass perihelion, when they are already receding and faint. By the time a mission could launch, the object is gone. The gap between detection and action frustrates planetary scientists, who recognize that each interstellar visitor is a unique scientific prize. Closing this gap requires pre-positioned fast-response spacecraft, possibly stationed at Earth-Sun Lagrange points, ready to deploy on short notice. Such infrastructure does not yet exist, but may become a priority as the catalog of interstellar objects grows. Combining all available datasets paints a picture. 3I Atlas is a compact object size of a small city, composed primarily of carbon dioxide ice with significant carbon-rich material, possibly graphite or complex organics. The surface exhibits low dust production, suggesting either low dust content or efficient dust retention. Outgassing occurs but concentrates in jets rather than uniform sublimation. Non-gravitational acceleration indicates active mass loss. Polarimetric properties hint at large grains or a rough regolith. Isotopic ratios suggest ancient formation, possibly 7.5 billion years ago. Trajectory aligns loosely with the ecliptic. High-resolution imaging remains pending. Each piece of evidence is a fragment of a larger puzzle. Individually, most observations admit multiple interpretations. Collectively, they constrain the possibilities. The challenge for researchers is synthesizing the data into a coherent model that predicts future observations. If the December JWST spectroscopy shows layered composition, different regions with distinct mineralogy, the fragment hypothesis gains support. If the spectrum is homogeneous, the comet model prevails. If thermal emission exceeds solar equilibrium, internal heat sources become plausible. If the surface temperature matches predictions, no additional heat is needed. The scientific method thrives on these binary tests. Propose a hypothesis, derive a testable prediction, gather data, compare. If the prediction holds, confidence in the hypothesis increases. If the prediction fails, revise the hypothesis or discard it. The December observations will perform this function for 3I Atlas. Until then, uncertainty dominates. Researchers issue careful statements hedged with caveats. Media coverage oscillates between sensationalism and caution. The public watches, intrigued but confused by the conflicting narratives. What remains undeniable is the significance of the object regardless of interpretation. If it is a comet, it expands the known diversity of cometary compositions and challenges models of protoplanetary disk chemistry. If it is a fragment, it opens a new field, exoplanetary geology through natural sample return. Either outcome advances knowledge. The worst scenario would be inconclusive data, leaving the mystery unresolved and forcing a wait for the next interstellar visitor. Here's where the stakes escalate. If 3I Atlas is confirmed as a planetary fragment, it validates the existence of a vast reservoir of interstellar debris, remnants of billions of years of planetary system formation and destruction across the galaxy. This reservoir becomes a potential resource. Future technologies might enable interception and capture of such objects, bringing them into stable orbits for mining or detailed study. A 14-kilometer rock ice composite contains trillions of tons of material, water, carbon, metals, far exceeding the total mass of all spacecraft ever launched. Accessibility is the challenge. Matching velocity with a fast-moving interstellar object demands enormous energy, but the long-term vision of interstellar resource utilization begins with recognizing that the resources exist and occasionally come within reach. Security considerations emerge as well. An object the size of 3I Atlas impacting Earth would release energy equivalent to millions of nuclear weapons, causing global catastrophe. Current surveys aim to catalog near-Earth asteroids to provide warning of potential impacts. Interstellar objects arriving with hyperbolic velocities from unexpected directions evade early detection. 3I Atlas was discovered months before perihelion, sufficient time to characterize its orbit and rule out impact. But a future interstellar visitor might not be so benign. Enhancing detection capabilities to find these objects years in advance becomes a planetary defense priority. Observing teams have submitted proposals for JWST, Hubble, and major ground-based telescopes, coordinating a multi-wavelength campaign. JWST will allocate 20 hours of observation time. Hubble will attempt high-resolution visible imaging to resolve surface features. VLT will provide adaptive optics-corrected spectropolarimetry. Keck Observatory will contribute near-infrared photometry to track brightness variations. ALMA may attempt millimeter-wave imaging to map molecular emissions. The data will flood in over a 48-hour window as Earth's rotation brings different telescopes into optimal viewing geometry. Analysis will take weeks. Spectral line fitting, thermal modeling, composition inversion, and morphological reconstruction all require careful calibration and cross-validation. Preliminary results might appear in astronomers' telegrams within days, but peer-reviewed papers will take months. The scientific community will debate every detail, testing interpretations against the data. Consensus, if it emerges, will come slowly, built on reproducible findings and independent confirmation. The broader public, meanwhile, faces a different experience. News outlets will cover the December observations, likely emphasizing the fragment hypothesis due to its novelty and dramatic implications. Headlines will speculate about alien planets, ancient relics, and cosmic mysteries. Scientists will issue cautious statements urging patience and emphasizing uncertainty. The gap between scientific caution and public fascination will generate friction, as it often does with ambiguous or incomplete data. Misunderstanding and hype are risks, but so is dismissiveness. The truth lies in the data, and the data will speak in December. If the observations confirm unusual features, layered composition, thermal anomalies, complex organics, the fragment hypothesis transitions from speculation to working theory. Follow-up studies will intensify. Detailed modeling of formation scenarios, searches for similar objects in archival data, proposals for future intercept missions. If the observations show ordinary comet characteristics, the anomalies observed at perihelion will be reinterpreted as artifacts of viewing geometry or instrumentation limits. Either way, the field advances. One element remains conspicuously absent from the narrative: any signal of intelligence. SETI protocols require checking interstellar objects for radio emissions or other indicators of artificial origin. Observations thus far show none. The object does not transmit. It does not maneuver beyond what outgassing explains. Its shape, insofar as it can be resolved, appears irregular, not geometric. No spectral lines from industrial pollutants or synthetic materials appear. The hypothesis that 3I Atlas is an artifact lacks supporting evidence and gains no traction among researchers who specialize in such searches. The object appears natural, albeit unusual. Philosophical implications compound as the data deepen. If interstellar space is littered with planetary fragments, the galaxy becomes an interconnected web. Material ejected from one system drifts for millions of years, potentially seeding other systems with organic molecules or even microbial life. Planetary systems are not isolated laboratories but nodes in a galactic network, exchanging matter and information over cosmic timescales. This perspective shifts thinking about life's origins from a purely local question, how did life arise on Earth, to a distributed question, how does life propagate across the galaxy? No definitive answer exists yet. Detecting life or its precursors in an interstellar object would provide the first clue. Even negative results constrain the hypothesis. If ancient fragments show no organics, panspermia becomes less likely. The December observations of 3I Atlas will contribute one data point. Future interstellar objects will add more. Over decades, a statistical picture will emerge, revealing whether complex chemistry is common or rare, whether isotopic compositions cluster or vary wildly, and whether any objects show signatures inconsistent with natural processes. Imagine the moment when the first December spectra download from JWST. A researcher opens the file, plots the data, and sees what? Strong absorption lines from water ice, undermining the CO2 hypothesis, or confirmation of carbon dioxide dominance, supporting the fragment model, or something entirely unexpected. Methane bands, ammonia features, complex organics, spectral signatures with no immediate identification. The reaction might be excitement, confusion, or both. Preliminary interpretation begins immediately, cross-referencing databases, running models, consulting colleagues. Within hours, preliminary findings circulate informally. Emails, Slack messages, phone calls. Within days, an astronomer's telegram posts announcing the detection and inviting independent confirmation. Within weeks, a preprint appears on AR Crime, presenting the data and offering cautious interpretation. Within months, peer review concludes, and a paper publishes in Nature or Science or the Astrophysical Journal. The process is orderly, built on established norms, yet each step crackles with tension as new information filters through the community. The waiting period between now and December tests patience. Researchers analyze existing data, refine models, prepare observing proposals. Instrument teams calibrate and test. Public interest simmers, stoked by occasional news updates and social media speculation. The object itself, indifferent to human attention, continues its trajectory, outbound from the Sun, cooling as solar heating diminishes. By December, it will be 270 million kilometers distant, a challenging target but within range of the most sensitive instruments. Consider the mechanics of the December observation. JWST orbits the Sun at the second Lagrange point, always keeping Earth between itself and the Sun. To observe 3I Atlas, the telescope will orient toward a point in the sky roughly 60 degrees from the Sun, well within its operational limits. The near-infrared spectrograph will collect light across wavelengths from 0.6 to 5.3 microns, capturing absorption features from water, CO2, methane, ammonia, and complex organics. Integration time will be several hours per target, split across multiple configurations to cover the full spectral range. The resulting spectra will have signal-to-noise ratios exceeding 100, sufficient to detect trace constituents at the parts per million level. Ground-based telescopes face greater challenges. Atmospheric turbulence blurs images, limiting resolution to about 1 arc-second without adaptive optics. With adaptive optics, resolution improves to near the diffraction limit, around 0.05 arcseconds, enough to resolve 3I Atlas as a small disk. Spectropolarimetry will measure how polarization varies with wavelength, revealing grain size and composition in the surface layers. Photometric monitoring will track brightness changes as the object rotates, which takes approximately 8 hours based on preliminary light curve analysis. Brightness variations indicate an irregular shape or surface features with different reflectivity. All this data will converge in December, creating a comprehensive portrait of 3I Atlas. If the results are ambiguous, the scientific community will settle into long-term analysis, debating interpretations, and awaiting the next interstellar object. If the results are definitive, confirming either the comet or fragment hypothesis, the impact will be immediate. Textbooks updated, models revised, future missions designed to target similar objects. The fragment hypothesis, if validated, opens specific research avenues. Geologists will compare 3I Atlas's composition to meteorites and lunar samples, looking for analogs or entirely new mineral phases. Isotope geochemists will model the nuclear processes in the parent star, constraining its mass and metallicity. Planetary scientists will simulate the collisional or tidal disruption that ejected the fragment, testing whether such events are rare or common. Astrobiologists will assess whether any organic molecules detected could relate to prebiotic chemistry or even biology. The study of 3I Atlas mirrors modern science, data-driven, interdisciplinary, and global. Researchers worldwide contribute observations and analysis, sharing data openly to accelerate discovery during the object's brief visibility. Yet, if December's results defy both comet and fragment models, revealing strange spectra, structures, or thermal anomalies, the reaction will be immediate. Science advances through such shocks, but extraordinary claims demand extraordinary proof, sparking scrutiny and debate. Scientists, invested in familiar frameworks, may resist disruptive data. As with Oumuamua, early excitement could devolve into controversy before consensus forms. Communicating uncertainty to the public will test researchers again, for science rarely offers tidy answers. Meanwhile, 3I Atlas itself drifts through its immense history, a relic born 7.5 billion years ago around a lost star, ejected after cataclysm, and frozen for eons in interstellar darkness until the sun's gravity drew it inward. Humanity now observes it for a fleeting moment before it vanishes again. Such encounters reveal both the grandeur and transience of cosmic exploration, each observation a brief flash of understanding in an endless night. Whatever December reveals, comet or fragment, the data will endure, expanding knowledge of planetary origins and interstellar chemistry. The object's discovery proves how collective investment in science yields meaning from chance. As instruments ready and expectations rise, 3I Atlas reminds us that discovery is both empirical and poetic, a small civilization catching light from a